Hello, this is Captain Chaudhari. In my series of videos on basic stability calculations, I was doing damage stability calculation. The damage stability calculation for the box vessel is explained or done with constant displacement method, which I started in my last video, and in last video I discussed damage to a compartment which was completely filled with homogeneous cargo. Now here we are just for understanding sake, it's not that practically we carry cargo like that, but just for understanding sake, trying to understand the various ifs and buts of damage stability, let us consider this yet another problem from my book that is categorized under damage to a compartment below the watertight flat. And this compartment is just above the keel and below the watertight flat. So let's say there is a ship 80 meters in length, 80, and 16 meters this way. There is a central compartment 12 meters. This ship is floating at a draft of 4.5 meters, and at 4 meters above the keel there is a watertight flat, and here is this compartment full with homogeneous cargo of permeability 70%. Now this flat is at 4 meters. Now kg is 4.72 meters. As we know, kg in case of constant displacement calculation does not change after the damage, provided the compartment has got a dry rigid cargo or it is empty. So now in this case there is a dry homogeneous cargo of 70% permeability. Now there are certain advantages in this particular kind of bilging. Advantage in the sense like advantage towards the stability, and that advantage is the water plane area as well as moment of inertia is not lost, because this is the initial draft. Probably this is going to be the final draft, and you can see that the damage remains below the watertight flat, right? So damage also remains below the final water line. So what is the loss buoyancy? Loss buoyancy should be equal to 12 into 16 into 4 into 0.7. So this is the loss buoyancy, 537.6 meter cube, right? And intact water plane area should be 80 into 16, because the water plane area is not going to be breached, so it is 1280. Okay, so sinkage can be found out very easily. Sinkage will be loss buoyancy upon intact water plane area. So 537.6 divided by 1280 gives me 0.42. So new draft will be 4.5 plus 0.42, that is 4.92 meters. Although the vessel is box type, but the damage is not vertically uniform. Why I say damage is not vertically uniform? Because between the keel and final water line we have the presence of watertight flat which is doing its duty. It's not allowing the damage to go above the flat level. So damage is not vertically uniform. So we cannot say that kb is half of the draft, right? So what we need to do in the next step is to find out what is the new kb. To find out the new kb, we need to take the moment. So we can say checking moments of volume about keel and volume up to the new water line. So it is 80 into 16 into 4.92, and I enclose the volume, multiplied by half the distance to the keel, that is 4.92 divided by 2. This is the moment of total volume regardless of what is damaged and what is not damaged. Now I subtract 12 into 16 into 4, this volume which is damaged, right? And I take the moment about keel, so it will be 4 divided by 2, right? That is the distance to the keel, but because it is damaged, I'll have to multiply this with the permeability 0.7. Now this whole thing divided by intact underwater volume, that is 80 into 16 into the initial draft, that is 4.5 meters. Let's see how much you get. So it is 80 into 16 into 4.92 into 4.92 equals, divided by 2, minus, in the bracket, 12 into 16 into 4, 7 bracket closes, equals, divided by, gives me 2.503. 2.503 meters is the KB1. Now BM transverse. Now BM transverse is residual moment of inertia of the water plane area about the fore and aft axis passing through the center of flotation. Yes, that is the residual moment of inertia, divided by intact underwater volume. Now the thing is, there is no loss of moment of inertia because the damage is not reaching the final water line. So let us say the residual moment of inertia therefore is equal to total moment of inertia, and total moment of inertia is 80 into 16 cube divided by 12, right? Divided by intact underwater volume, that is 80 into 16 into 4.5. That is the initial underwater. I'll put that thing here also. So BM transverse is equal to 80 into 16 cube divided by 12 divided by 80 into 16 into 4.5, and that is equal to 80 gets cancelled, that is 16 square upon 12 into 4.5, 4.741 meters, that is the BM transverse. KB, which we have got, is 2.503. So the total of the two km transverse is 7.244 meters. Now kg, which was given in the question, is 4.720. So the GM would be 2.524 meters. So we have found out the sinkage, we have also found out the GM. The point to be noted here is the water plane area does not change, it does not get damaged, and it's a box vessel. So please understand, by a simple philosophy, if the water plane area does not get damaged, it means there is no loss of moment of inertia. Underwater volume also is not changing because intact underwater volume is same. So when we say BM transverse is equal to moment of inertia of the water plane area divided by underwater volume, the BM should not change. So in every case where the water plane area remains constant, like in this case box vessel, where the water plane area is not even damaged, then can we say in constant displacement calculation the BM does not change. One golden rule we must always remember, that KB in a bilging calculation will always increase. Now before the damage, KB was half of 4.5, that is 2.25, and after damage you can see it is more than 2.25, it is 2.503. So center of buoyancy always rises in a bilging calculation, which is good for stability because it is indirectly also increasing Km, right? Because Kb increases, there is a chance that Km would increase. And in this question, while Kb is increasing and Bm is constant, can we say that Km has increased compared to the original value? And if the Km has increased and as per the constant displacement method, Kg has to remain constant, it means that in this numerical, the Gm has increased. So please understand this golden rule. This is for your survival. This, as a mariner, you must know. Every damage where, every case of bilging where the damage does not reach the final water line, the stability of the ship must increase. Stability of the ship must increase. Right? And if the damage reaches the water line, that means there is loss of moment of inertia. Then you have to do the calculation to find out whether the stability will increase, decrease, or remain same.